Hi everyone, this is Mike Graham from the Mazingira Center at ILRI. Just wanted to follow up after my presentation on modeling and scaling up for agriculture and livestock in Eastern Africa from last week's government training session for the program for Climate-smart Livestock. So what I wanted to get into today was to follow up on that session. I talked a lot about modeling, and I think modeling can be intimidating for a lot of people. So what I wanted to do was actually, and we didn't have time to get into this, was to kind of demystify modeling a little bit and take away some of that intimidation factor. And we could do that because models, although some of them can be quite complex, many of them are actually quite simple. So what I wanted to do was demystify modeling with a simple mathematical modeling exercise. First of all, I would talk about the type of model we're going to use. So the type of model we're going to use is called a simple linear regression model. So a simple linear regression model uses an equation, which is a simple linear regression equation, to predict the values of one variable from values of a second variable. In this particular case, we are going to be predicting methane production on a daily basis in grams per day from dry matter intake from cattle in kilograms per day. So this is actually a very common modeling exercise in livestock science where you predict methane production from dry matter intake, or DMI. So this is actually very common, so it'll be interesting for people to see, hopefully, how this is actually done. And this is just one of the ways we can use modeling as a potentially powerful tool for looking at predicting methane or other greenhouse gas emissions from other variables related to livestock. So that's kind of the basic setup for what we're going to do here today. Is use one of these simple linear regression models that rely on an equation. Part of what we're going to do is use some variables, in this case the dry matter intake or DMI, to predict or calibrate the model, and that predictor variable is going to be called the independent variable. So that's DMI, and that is the variable or number that we are going to use to calibrate the model. And we're also actually going to use some of our data for for methane production as well. But in general, the variable you're using to predict the other variable is called the independent variable. On the other hand, the variable you're predicting is called the dependent variable. So in this case, we want to use DMI to predict the methane production in grams per day, and that's going to be the dependent variable, or y. So you have the independent variable here on the left side of the screen in this column, and that's usually labeled as x, and then y is the dependent variable, which in this case is methane. And in general, we also want to, with some of this data that you're seeing on the right-hand side of my screen, some of that data is going to be, so this is a small subset of the data, so we're actually going to want to withhold some of the data from calibration in order to validate what we call validate the model, which is basically what we want to do is use some of the data that we have and keep it out of our model so that we can check to see if the model actually did what we thought it was going to do. So I'm going to give you a little more background, and then we're going to do a worked example of this in Excel. Okay, so again, a regression equation. So the simple linear regression model uses what we call a regression equation, as I mentioned, and this is the basic structure of a regression equation. So you have the dependent variable y is equal to mx plus b. So again, the y is the dependent variable, which in this case is going to be methane production, and x is going to be the independent variable, or DMI in this case. So the formula for this is pretty consistent throughout modeling for simple linear regression. This is basically the equation that you're always going to want to use, is y equals mx plus b, this basic format. And I can show you a little example here. So this is, again, a partial data set for the model, and we're going to use DMI to predict methane. Again, with x, DMI being x, or the independent variable, and y being the dependent variable. So what happens now? So once we plot the data, so this is a plot of the data we just looked at with more data, obviously, and this is just plotting the methane emissions on the y-axis on the left side of your screen, and the dry matter intake, or the x-axis, in grams per day on the bottom of your screen. So this is just a simple plot of basically an expanded version of the data we just looked at. And when we get out of that as a line, and in this case, we call the line that is produced from this plot a regression line. So you can see there are points that are scattered about it, but we get out of this a regression equation for methane production versus dry matter intake. So the equation that we get comes in the form of y equals mx plus b. You can see here on the right-hand side of the screen. So you have y, which is the methane that's being predicted, and then this 0.037 is the slope, and then you have the x for the dry matter intake, which we will get into a little bit later where that comes from, and then you have plus 32.7, which is what we refer to as the y-intercept. So you don't really need to know that for this, but I just wanted to show you that this equation takes the form of a line, and that line has a certain form that we can then use in modeling. And this is the standard equation that we want to use when we're doing a simple linear regression model. And this is just the numbers you're seeing on your right here are not universal. These are just the numbers that we got using this particular model. So I want to run through the Excel exercise a little bit now that you're up to speed on what is involved with a regression equation, how does it work, and how does it work in terms of having some data being withheld and some data being put in for calibration, validation, and then you have things with independent and dependent variables. So I'm going to go to Excel now, and we're going to look at first, we have a sheet that has all of our data in it. So you can see here that this sheet contains, in column A, you have the dry matter intake in kilograms per day, and then in column B, we have the methane production rate in grams per day. So this is actual data taken from chamber measurements of animals at Mazingira of the dry matter intake per day, and then the methane production rate that was associated with that animal for that amount of dry matter intake. So this is going to be based on real data, and we're going to try and use this real data to create our model. So we only have these two columns, and this is all we're going to use to try and predict methane production. So you can see we have dry matter intake, methane production, and we have a total of, 120 data points. So we have 120 total data points, and what we're going to do is we're going to split this data into two, or into half. So we're going to take half the data and make it what we call calibration data, and the other half the calibration data is what we're going to use to predict the model, to calibrate the model, I should say, and try and predict methane production from DMI. So we're going to use this data to create our regression equation. We're also going to have something called the observed data, which is the other half of the data. So this is going to be the data that is withheld. As you can see, whatever in here, this is withheld from the model. And this is the data we are keeping out of the model so that we can check later to determine whether or not our model actually worked the way we expected it to, and that's what we call validation, or model validation. So let's go back and look at the first step here. So, and I'm going to send you this. I should specify here that I will definitely send you this Excel sheet so you can try and do this on your own. So the first step here is we want to take this calibration data that we're going to use to calibrate this model and follow the instructions here, which is to copy and paste into the prediction model tab here all the data for DMI and methane production here. So I'm just going to quickly select that, and I'm going to hit copy. And then I am going to go to the prediction model tab where we have step 1 continued, and you see here it says enter calibration DMI, enter calibration methane. So I'm just going to paste values, or I'll just do paste actually, and we'll just paste the calibration values into the prediction model. So you can see that the prediction model only has 60 points of the total 120 or so that we had in the original full data set. So now when I paste that into when I finish step 1 here, this is a continuation of step 1, once I paste that in, you can see that it automatically generates this chart. And this is, again, methane, like the example I showed you in PowerPoint. This is a real example of a plot of dry matter intake versus methane emission rate. And from this, we have generated a line that contains all our data points for the calibration data. And we have generated also, you can see here, if I make it bigger, so this is the regression equation here. So this y equals 21.036x plus 46.767. That's going to be your y equals mx plus b. And then you have this r squared, and I'll get to into that a little bit later, but r squared is a measurement of how good your x or independent variable is at explaining the predicted variable, which is methane, in this case, your independent variable. So basically, this is kind of how good or accurate, r squared is how good or accurate your model is at describing the data. And it usually ranges from 0 to 1, with 1 being the best and 0 being the worst. So in this case, 0.8251 is actually a pretty good r squared. So I'm kind of happy to move on with this. And what we want to do is go to the next step, which is to take this regression equation. So if we look over here, you can see the full instructions. So here we want to take the right-hand side of the equation, which is the mx plus b part, which is this 21.036x plus 46.7, or 46.8 or so if we're rounding up. And we're going to copy and paste that. So we're going to first copy it, step 2. So copy, make sure I copy this. And if it wants me to make some edits here, I'm going to just hit the copy button. So I use Control-C to copy because it didn't want me to do that. And then what I'm going to do is, the next step is to paste the text into the right side of the regression equation in cell C in the model validation sheet. So the model validation sheet is right here. So if we go to the model validation sheet, we can look at column C, and we look at C2, and it says enter the prediction equation from the prediction model. And what we're going to eventually want to do is substitute the cell number in column B for X in our equation. So in this case, we'll delete this, and we'll do equal sign to set up our cell equation. And then we're going to paste what we just copied from the regression equation. And then you see we still have the X in here. So in following the instructions, we want to substitute the cell next to this one in column B. So what we want to do is do star or asterisk to multiply. And then we're just going to click over here on this cell, which doesn't have anything in it yet, and that's going to show a formula that will actually work in Excel. So it's now going to multiply by the value in cell B2 to get a prediction for methane from this regression equation. So I'm going to add some parentheses here to close this, and then I'm going to hit enter. So that gives us our regression equation here following these instructions. Now right now, it's showing us nothing because it's showing this error value because we haven't put anything in here. So we're going to put something there in a minute. But first, let's take this equation and have it be the same for all these cells, so that when we paste our values into column B, then all these cells will automatically update at work. So we're done with step 3, which was pasting these cells and substituting X in B2, for example. So we're done with step 3, and what we want to do now is do step 4. So for step 4, we're actually going to go to observe data, and this we are going to take the dry matter intake from the observed data, and we're again, like we did before, we're going to copy and paste this. So we're going to go down all the way to the bottom for the observed data. I'm going to hit copy, and again, this is the data on DMI that was withheld from the model, so we didn't use this in the prediction model. We're using this to validate the model. So this is not been used yet, where we're using this to make sure the model works. And then we're going to go back, and after we've copied the dry matter intake values for the observed data, and go to model validation. And what we're going to do is paste the observed values for DMI in here. So we can just hit paste, and it'll automatically copy the values in. And now you can see that instead of an error in column column C, what you now see is an actual estimate or predicted methane production value. So based on the observed data, which the model hadn't seen before, that we hadn't used at all, we can now use that data to plug into our equation that we got previously from the prediction model using this simple linear regression equation, y equals mx plus b, where we substitute in this value 8 or 7, depending on which cell you're in, to predict the methane production from the dry matter intake. So in this case, we entered in 8 for the observed dry matter intake and entered it into this formula as B2, and the predicted quantity of methane produced on a given day in grams per day was 215 grams of methane per day. And you can see that it automatically updated it for all those values for all the cells that we pasted the formula into. So that's the end of step 4. So where we just pasted data into the correct column here. It's column B for the DMI. And we're going to go to step 5. And step 5 is again in the observed data. So what we're going to want to do is check, before we do that, first check. So what we're going to want to do here is, so we have this predicted methane, as I mentioned, based on the equation that we just created and using the observed dry matter intake. And we want to see how close that was to being the reality. So each of these points in column B for observed dry matter is associated with a real value in the observed data. So in real life, the 8 kilograms of dry matter per day was associated with a methane production rate of 239 grams per day. And then, for example, the dry matter intake of 7 kilograms per day was associated with a methane production rate of 237 grams per day. And if we go back and look at the model validation, we can see that for 8 kilograms of dry matter per day, our model predicted 215 grams per day in terms of methane. So 215 here versus in the observed data we got 239. So it's about it's more than 20 off in terms of grams per day relative to what happened in reality is what our model is predicting. So our model is off by about more than 20 grams per day. How good is that? Well, I'll show you how well that actually stacks up in a moment. But the first thing we're going to do is go back to our observed data and complete step 5. So step 5 is we're going to take the observed methane production rate and paste that, copy first, and then we are going to copy the observed methane data and paste it into our model validation sheet so that we can compare, so we can do what I just did, which is compare this methane data that we predicted from our equation versus what we got in reality. So if we paste this in, you can again see that over here we have the dry matter intake and the methane predicted from our equation, and then over in this column you can see for each of these values, you can see that, for example, 239 that was off by a bit, this one was off by a bit. So you can see in column E how much it was actually off by, or how close it actually got. So for example, on row 4 here, we predicted that it would be based on a dry matter intake of 10 kilograms per day, we predicted that it would be 257 grams per day of methane produced. And what was actually found in real life was 256 grams per day of methane produced. So that's actually quite close. So we got very close to the real amount of methane produced by that amount of dry matter intake for one of our cattle at Mazingira based on our equation. So we have all this pasted in here, but what does that actually really mean? So you probably saw that when I pasted in all that data, that we got this chart. So the chart automatically updated, and this is a chart of, on the y-axis, or the left-hand side, is the measured or observed. This could really be called the observed methane production, which is our column E here, versus the predicted methane, which is our column C, where we actually, so it's looking, so this is a plot of the values for what we actually observed versus what we predicted based on our simple linear regression equation that we've gone through in this exercise. And it also shows you here the regression equation that's associated with this plot, because this is also a line, and then also the R-squared value. So again, the R-squared is a measure of how well the model we've created fits the data or describes it, and it goes from 0 to 1, with one being high or better and 1 being the best fit possible. So a value, an R-squared value of 0.86 is actually quite good. You can see it's a bit scattered here, but we have a fairly good fit in terms of the R-squared value. So I'm actually quite happy with that in terms of our model fit. So that means that our model did a reasonably good job of fitting the data. So for instance, if we want to look at another example, we can go back to the PowerPoint and look at two separate examples. So for instance here, let me navigate. So on the left-hand side, you have something that's pretty similar. Oh, sorry, this is not the... So on the left-hand side, you have something that's pretty similar to what we got in that from our actual data, but we're looking at methane production rate versus dry matter weight. You can see that the data, the points are clustered relatively close together for one data set versus a second data set where points are much more spread out. So you can see that the R-squared for the first data set, where the points are closer together, has a much higher R-squared and a much better fit of the model compared to the one on the right. So the one on the right, the points are more scattered out, and the fit is not as good as on the left. And for that reason, it has an R-squared value that is much lower when we're looking at the model. So the R-squared value for this model, which again is methane versus dry matter intake, is an R-squared of only 0.32, which is quite low actually, so that's not a very good, strong relationship, and we probably wouldn't want to use that if we were actually using this particular model in real life. But the model we've come up with, again, yes, you can see here, one of them has a much greater scattering of the data than the other, based on the circles I've drawn here. One is fairly narrowly clustered around the line, whereas one is scattered kind of all over the place. So I think that gives you kind of a general sense of modeling and how we might go about measuring it, and how we can use not only measuring it, but how we can use just one or two points or one or two points of data and extrapolate those for one type of data, for instance DMI, to predict methane production. And we used a fairly simple method to do this, using the simple linear regression equation, which is just a simple y equals mx plus b equation, which we then used to develop an equation to predict methane from DMI. And we found that the R-squared value, which measures how good our model is, essentially was high, indicating that our model was a good fit. So I am fairly happy with our model, and after validating it, it shows that it is a reasonably good model for predicting methane emissions from DMI. And I leave it to you to follow up with questions. I will be sending out the Excel file that goes along with this, that will be blank, and you can do it from the start by yourself. So it's really up to you where you want to go from here in terms of how you want to do the exercise. You can just watch the video, or you can go through the exercise, send it back to me, and let me know if you have any questions. So hopefully this exercise has been illuminating for you or helpful in some way, please let me know if you have any questions. Again, my email will be sent out as part of this exercise so that you can find me and contact me if you have any more questions. So thank you very much for listening and watching. I appreciate it. Have a good day.